18.7 is on electrolysis, which is definitely one of my favorite topics. This is electrolysis in chemistry is defined as the process of using electricity, electrical energy, to drive a non-spontaneous reaction. That just means that we're forcing it to happen. A non-spontaneous, not just any non-spontaneous reaction. That's what I said originally. Process of using electricity to drive a non-spontaneous redox reaction. Technically, electrolysis, if you break the word apart, it means breaking something with electricity. That's the electro part is with electricity, and lysis is our suffix for breaking or splitting. But this is not necessarily a splitting or a breaking process. It's just a process of using electricity to move a redox reaction in the backwards direction. We're going to look at 3 different types of electrolysis, 3 different ways that you can do it. And electrolysis is actually remarkably simple. You can safely do electrolysis at home if you wanted to. And the first type of electrolysis that we're going to look at that you're probably not going to be able to do at home is called the electrolysis of a melted ionic compound. For all 3 of the electrolysis reactions that we're going to look at, the setup is exactly the same for all of them. The only difference between the 3 different types is the substance that's actually being electrolyzed, that's being reacted with. So the setup for electrolysis looks a lot like the setup of a galvanic cell. I'm going to draw a beaker. One way that electrolysis is different from a galvanic cell is that we only have one compartment. We don't have to separate the 2 half reactions from each other. In fact, we can't separate the 2 half reactions. We need them to be together. We still need to have 2 electrodes, an anode and a cathode. So here I have a beaker, and I'm putting an anode and a cathode into my beaker. And if this was a galvanic cell, you know that we would connect the 2 electrodes together with some sort of wire. And because a galvanic cell is one that produces electricity, we would usually put something in the middle of the wire, something that would measure the electricity as it was moving from one electrode to the other. And we talked about how you could just put a voltmeter in there to measure the electricity, or you could put like a little light bulb or something that would light up as the electricity flows. So inside this electrolytic cell is what we call it, because this is going to be the electrolysis of a molten ionic compound. We're going to be filling this thing up with, the example that we're going to use is liquefied sodium chloride. So this is NaCl liquid. This is not aqueous sodium chloride. It is not NaCl in water. This is, you get a beaker and you put a bunch of solid salt in the beaker, solid NaCl, and then you put a Bunsen burner underneath it and you cook the crap out of it, heat it up until it gets so hot that the NaCl liquefies. That's a very high temperature. This particular reaction, the electrolysis of liquefied NaCl, works best if you have a pure carbon anode. So this would be like a graphite would work. And you have an iron cathode. And determining the ideal metals or substances for the electrodes, the anode and the cathode in electrolysis, a lot of it is just trial and error. It's not the same type of selection process as we would use in a galvanic cell. In a galvanic cell, we're trying to match the anode and the cathode with the components of the galvanic cell. In electrolysis, we're just trying to find an anode and a cathode that are good conductors of electricity and that won't give us any side reactions that are unwanted. So the last component that this electrolytic cell needs is some source of electricity. Because this is not going to be producing electricity, it requires electricity. And so the electricity is going to come into place up here. This is where we will connect the electrolytic cell. We can just put a battery in this spot right here. Or maybe if you're feeling brave, plug it in. I'm just going to use a battery. We're just going to use a battery, and that battery is going to have voltage that will drive this cell. So this is our electrolytic cell. And the electrons are going to move this way, and they're going to move this way. And they're going to go down like this, and then they're going to go up, and they're going to go like this. So that's the circuit that we've made here. For this particular electrolytic cell, the reaction that's taking place is the liquefied sodium chloride, 2 of them, 2 NaCl liquid, being converted into 2 sodium atoms, not ions, which are also going to be liquid because it's really hot, and a molecule of Cl2 gas. And this is the purpose behind doing this type of electrolysis. This type of electrolysis is really useful for synthesizing pure metals like pure sodium metal, which maybe is not that easy to find. And so this is why a person would want to do this type of reaction. And again, this is probably not one you're going to be able to pull off at home because you're probably not going to be able to liquefy sodium chloride. If you do, however, if you do want to do this at home, please be careful because you are going to be generating chlorine gas, which you definitely don't want to breathe. So you want to make sure that you're doing this in an area, in a spot where you have really great ventilation and there's no hazard. Just don't do this at home. As I'm talking, I'm thinking, just don't do this at home. So here are the half reactions that are taking place. The half reactions are, so in that NaCl, even though it's not aqueous, it is still does still contain ions. So we have liquefied sodium ions, and the liquefied sodium ions are being converted into liquefied sodium metal. And let's think about how the electrons would fit into this redox reaction. It looks like we would need to have 2 electrons reacting with the 2 sodium ions to get the liquid sodium metal. Our other half reaction is the 2 chloride ions, and they are also liquefied, not aqueous, liquefied. And they are reacting to produce Cl2 gas, and that's also giving off 2 electrons. So those are our half reactions. Now, if you were trying to do this at home, even though I told you don't do this at home, if you were trying to do this at home, before you could do this, you would need to know how big of a battery would you need to plug into this electrolytic cell for this reaction to take place. A scientific way of asking that question is, how much voltage do you need to drive this reaction? How much voltage is necessary? How big of a battery do you need to make this happen? And the way that we would calculate the necessary voltage for this reaction is exactly the same way that we would calculate the voltage being given off in a galvanic cell. It's just an E-cell calculation. Assuming that this is a standard cell, we're still just going to do cat minus an, cathode minus anode. And we are going to figure out which is which using our tricks, red cat. So this is going to be The E cell is going to be the reduction half reaction minus the oxidation half reaction. So all we have to do is go to that table of voltages of the half reaction and look up the voltages for our two half reactions. So let's go to that table. Let's go find it. I've got the one where we're in alphabetical order, and I'm looking for, I've got chlorine right there, and it is 1.35827. 1.35827. And now let's go find our sodium voltage. Sodium voltage is down here, negative 2.71. Negative 2.71. So let's plug these into our E cell reaction. And so we've got reduction minus oxidation, oil rig. Oxidation is loss, so oxidation is the reaction where electrons are being produced as products. Reduction is gain, so reduction is the half reaction where we are adding electrons. So here is our reduction reaction, and here is our oxidation reaction. So our E cell is going to be negative 2.71 volts. Minus 1.35827 volts. And let's get our calculators and figure that out. Negative 2.71 minus 1.35827. The voltage of this necessary voltage is 4.07. Now you might be thinking, oh my gosh, we got a negative number here. I thought we were supposed to always be getting positive numbers when we're calculating E cell. Don't be tricked by this. E cell is, as you learned, is always positive for a galvanic cell. Always positive for a galvanic cell. And this is because when you build a galvanic cell, the electrons are going to move in the direction that they want to go. You can't tell the electrons which way to go. You can't force them to go in any particular direction, and they will always move in the direction that generates positive voltage. For an electrolytic cell, it's the opposite situation. In an electrolytic cell, you are forcing the electrons to go in the direction that they don't want to go. That's the purpose of the battery. That's what we're doing with the battery. We are making electrons move in the wrong direction. So for an electrolytic cell, the voltage is always going to be negative. It is always a situation where we are forcing electricity into the cell. I can't talk and write electrolytic at the same time. We are forcing the redox reaction to move in the wrong direction, and we are forcing the electrons to move in the opposite direction that they want to go. So when the question is, how much voltage do you need? You are always going to be getting a negative number. That's expressing how much voltage is required for the reaction to take place.